Hello, my name is Zwemer.
My name is Espayline Marcelin.
How much do you really know about marijuana?
And no, this is not a joke. Today I will tell you more about tetrahydrocannabinolic acid, which most of us know as THC or weed.
Now specifically, we are going to be investigating the structure and function of delta-1 tetrahydrocannabinolic acid synthase, the primary enzyme involved in the psychoactivity relating to cannabis sativa.
Most people are familiar with the plant cannabis sativa. However, many do not know that the plant produces over 70 different cannabinoids, which can be isolated from the leaves.
Now the most common cannabinoid is delta-1 tetrahydrocannabinol, or THC, which is known for being the primary psychoactive factor in cannabis. However, it is important to note that not all cannabinoids are psychoactive. So for example, CBD is a cannabinoid that is not psychoactive.
The cannabinoid of interest for our given enzyme will be THC. THC derived from tetrahydrocannabinolic acid. This occurs within the leaves of the cannabis plant.
Now, the THC first being derived from THCA is going to be a non-enzymatic decarboxylation reaction that occurs spontaneously when heat is applied. Thus, the primary difference between these two molecules is going to be this carboxy group off of the phenyl ring, or the lack thereof, on the THC molecule.
However, before this decarboxylation can occur, THCA must be biosynthesized from cannabigerolic acid, or CBGA. The enzyme that catalyzes this step is THCA synthase.
Now, THCA synthase mediates the biosynthetic step, which converts CBGA into THCA in order for THCA to then go on and be converted into THC.
Thus, THCA synthase is regarded as the key enzyme controlling the psychoactivity of cannabis.
Now, THCA synthase catalyzes the oxidative cyclization of the monoterpene moiety of CBGA. But how does it do this? This enzyme catalyzes the reaction primarily via a flavin binding site. Shown here is a stereo view for the tertiary structure of THCA synthase.
The FAD cofactor, flavin adenine dinucleotide residue, sits in the binding site of this enzyme.
Now, the overall mechanism was not yet completely understood before the Journal of Molecular Biology published a paper on the structure and function of delta-1 tetrahydrocannabinolic acid synthase. This peer-reviewed journal explored the structure and function of the enzyme in order to understand the overall enzymatic mechanism.
We will be presenting this article data in order to further explain the structure and function of the enzyme, and then with this knowledge, introduce the overall mechanism of the oxidative cyclization of CBGA to THCA.
Now, Yoshinari et al. Isolated the enzyme by overproducing the molecule in insect cells, then by purifying the molecule and then crystallizing it in order to study the structure and function relationship of THCA synthase.
In order to elucidate the detail of the mechanism of the enzyme, they determined its X-ray crystal structure and identified specific amino acid residues in the active site.
Now, first, this method was used to determine the tertiary structure of the protein, which is going to be shown here on this slide.
Of the 518 amino acids involved in the primary structure of the enzyme, 502 amino acids are included in the tertiary structure.
Now, THCA synthase is divided into two domains. So we have domain 1 and we have domain 2. Now, between the two domains sits the flavin binding pocket. In this binding pocket, the flavin adenine dinucleotide residue is bound by two covalent bonds to residues in domain 1.
Domain 1 is an interrupted domain based on its primary structure, made up of residue 28 to 253 and 476 to 545. It consists of 8 alpha helices and 8 beta strands.
Now, domain 2 is a continuous region of amino acids consisting of residues 254 through 475, and it's made up of 8 anti-parallel beta strands surrounding 6 alpha helices.
Domain 1 is further divided into two subdomains, subdomain 1A and subdomain 1B. Subdomain 1A is made up of residue 28 through 134 and consists of 3 alpha helices which surround 3 beta strands. There is a disulfide bond connecting alpha helix A and alpha helix C.
Now, subdomain 1B is made up of residues 135 through 253 and 476 through 545, and consists of 5 anti-parallel beta strands surrounding 5 alpha helices.
The residues of structural interest for catalysis were evaluated in the study by mutagenesis, which is how it was discovered that the FAD moiety is essential for the enzymatic activity.
Now there is a FAD residue sitting in the binding pocket between domains 1 and 2. So FAD is an electron carrier, which is characterized by its ability to aid in proton transfers, which facilitates its ability for enzyme catalysis.
In our enzyme, FAD has 2 covalent bonds to residue in domain 1. Shown in this graphic is the general domain binding region of FAD to the enzyme.
Now the first covalent bond is to 8-alpha-N1 histidyl, a covalent bond from the FAD isoalloxazine ring into a histidine residue in domain 1 of the enzyme. So we can see here that this yellow line is showing the domain 1 region of binding. Now the second is a disulfide bond, which is also from the ring, to a 6S-cystenyl, also in domain 1.
There are also many hydrogen bonding interactions, in addition to the 2 covalent bonds, which anchor the FAD residue to the binding site.
Now here we have a model of the protein with secondary structures that we can see here. Now each of these yellow halos presented are representative of a residue from the enzyme that will hydrogen bond to the FAD residue.
Here, we have eliminated the secondary structure for better visualization of the hydrogen bonding residues.
Now first, there are 5 main chain nitrogen atoms on the following residues, which will be involved in the hydrogen bonding. So for example, glycine residue 113 is located in domain 1A, along with histidine residue 114, which covalently bonds to the FAD.
Glycine residue 180 and tyrosine residue 175 are both in this category and are located in domain 1B. Additionally, there is hydrogen bonding between the nitrogen atoms on the side chain of the histidine residue 174 and the asparagine residue 483, both located in domain 1B.
Now finally, there's hydrogen bonding between the hydroxyl group of the side chain of tyrosine residue 190 and tyrosine residue 481, both located in domain 1B. Now the cysteine residue 176, shown here, is the residue which forms the disulfide bond, and it is also located in domain 1B. Now this enzyme involves base catalysis and is a class 1 oxyreductase enzyme.
The author compared the structure of the substrate and the product to further determine that there were 2 clearly defined steps that must occur in the oxidative cyclization mechanism.
So first, deprotonation of this hydroxy group here on the CBGA ring must occur through base catalysis. Then a hydride transfer from the CBGA molecule had to occur to allow the formation of a double bond, shown here. Now FAD is characterized to transfer electrons, specifically hydrides. So the researchers inferred that the hydride transfer was the role of the FAD residue in the binding pockets. However, it was unclear as to exactly which residue on the enzyme is located in the binding pocket and is responsible for that deprotonation of the hydroxy group. Therefore, they looked to enzymes that had similar protein structure and similar catalytic properties to THCA synthase in order to figure this out.
There are several enzymes within this description that fit the description. Berberine-Brach enzyme, glucooligosaccharide oxidase, and aclazinomycin oxidoreductase. Shown here in the graphic are the residues which aid the FAD in the catalytic activity for each of the similar enzymes.
Now, for instance, tyrosine residue 429 in the GOOX enzyme around the isoalloxazine ring of FAD is the catalytic residue which aids FAD in its respective reaction.
These enzymes were selected by Yoshonari et al. Due to their enzymatic activity which is similar to THCA synthase. They are so similar, in fact, that BBE has actually been seen in a similar study to catalyze the CBGA to THCA reaction itself, however, at a much slower rate.
So this here is actually the reaction of our reaction here, CBGA to THCA, but now this enzyme is BBE. But like she said, it was at a much slower rate. Now, in fact, it was also discovered that each enzyme had similar or the same residues as THCA synthase in the binding pocket, which respectively catalyzed their reactions.
In aligning their sequences, it was seen that BBE had a 39% identity to THCA synthase. GOOX has a 26% identity, and AKNOX has a 21% identity.
Now, through an RMSD study, which is a root mean square deviation study, Yoshinari et al. Were able to measure the similarity of the enzyme molecules by measuring the average distance between the atoms. So in this case, the smaller the RMSD, the more similar the structures are. Now, BBE had an RMSD of 1.7 Armstrongs, GOOX had an RMSD of 2.6 Armstrongs, and AKNOX had an RMSD of 3.3 Armstrongs. Now, this percent identity, RMSD, and the ability of BBE to catalyze the CBGA to THCA reaction, which is usually the role of our THCA synthase, but now occurs at a much slower rate, showed that BBE was the most similar protein to THCA synthase and was hypothesized to share the same catalytic residue on the enzyme.
Therefore, they decided to do a study in which they manipulated the THCA synthase molecule with point mutation for each of the catalytic residues correlating to the three similar proteins.
Thus, they could identify each of the catalytic residues from the similar enzymes and manipulate the corresponding residue in the THCA synthase to a non-reactive amino acid, and then examine the amount of change in the production of THCA in comparison to the wild-type enzyme. Now, this would be able to determine which residue is responsible for that that proton transfer in the mechanism.
One point mutated enzyme was tyrosine residue 484, changed to a phenylalanine residue, and another histidine residue 292 was changed to an aniline residue.
Now, in another molecule, tyrosine residue 417 was altered to become a phenylalanine residue, and in the last protein, our glutamic acid 442 was mutated or modified to become to have a glutamine residue in place. So they constructed and purified each enzyme, and the enzymatic activities of each were assayed by monitoring the conversion of CBGA to THCA using reverse phase high performance liquid chromatography.
It resulted that the glutamic point mutated enzyme resembled the one-type activity, which is in the standard made activity of at least 85%. This signified that glutamic acid 442 was not the catalytic residue.
Now, tyrosine 417 changing into a phenylalanine resulted still in a 42% activity. Histidine 292 changing to an alanine resulted in a 5% activity, which is pretty low, but it's not quite zero. Now, finally, tyrosine residue 484, which happens to be the catalytic residue in BBE, changing to a phenylalanine residue resulted in no enzymatic catalysis. Therefore, it was able to be concluded that the mechanism of CBGA to THCA, tyrosine residue 484, is the residue that will deprotonate the hydroxyl group at the O6 position prime of CBGA in a concerted mechanism with the FAD hydride transfer.
Here, we present a hand-drawn model of the base catalysis which occurred during the reaction.
Now, the oxidative ring formation reaction proceeds via an intermediate formed by the elimination of the hydride, shown here, on the C3 position of CBGA, which leads to the formation of a new single bond following the formation of this double bond here. And now the removal of the proton from the hydroxy group on the 6' position of the CBGA ring creates this ketone, which will then nucleophilically attack that double bond to form a new ether ring between carbon 6 and 8.
There is an overall mechanism. This here is the overall mechanism. We can see the tyrosine molecule, which will deprotonate the hydroxyl group, the side group amino on the histidine residue 292, which also in the active site of the enzyme will stabilize the carboxylic acid group of CBGA, creating charge complementarity.
Now, the tyrosine residue 417 hydroxyl group on the enzyme here will stabilize the hydroxy group on the CBGA ring via hydrogen bonding.
The amino group on the isoalloxazine ring will rip off the hydrogen. The FAD residue in the binding pocket is anchored by a disulfide bond with cysteine residue 176 of the enzyme, as well as the side group amino of histidine 114 of the enzyme.
Now, an imine group will be created in the FAD ring in order to stabilize the structure. Now, as the hydride transfer and the deprotonation occur, it actually brings the molecules into position to line up carbon 4 and carbon 8 of CBGA to approach carbon 3 and oxygen prime 6, which will subsequently cyclize the molecule into the desired product, THCA. Thank you all for watching, and thank you to Yoshinari et al. For their work on the structure and function of delta-1 tetrahydrocannabinolic acid synthase.